Look around you. What do you see? Perhaps you see a screen, a room, or the world outside your window, but I see data. Everything from the smallest subatomic particle to the largest galaxy generates information. This information, these countless bits of data, swirl around us like cosmic dust. Data analysis is our attempt to make sense of this swirling universe of information. It's like being an astronomer, but instead of looking at stars, we look at numbers and patterns. We are all data explorers, whether we realize it or not, trying to navigate the vast oceans of facts and figures that surround us every single day. It is a fundamental human endeavor. Why is this so crucial, you ask? Imagine trying to navigate the cosmos without a telescope or a star chart. You'd be lost, wouldn't you? Data analysis provides us with the tools, the telescopes, to understand our world, our businesses, our health, and even ourselves. It helps us see patterns that are invisible to the naked eye. It allows us to make informed decisions instead of just guessing. Without data analysis, we are merely drifting through a sea of raw information, unable to chart a course or understand the currents. It transforms raw, chaotic data into meaningful insights, guiding our path forward. Think about the weather forecast you checked this morning. That forecast is a product of immense data analysis. Scientists collect data on temperature, pressure, wind speed, and humidity from countless sources around the globe. They then use sophisticated models, a form of data analysis, to predict what the weather will be like. This allows you to decide whether to carry an umbrella or wear sunscreen. This simple daily act is powered by the rigorous examination of vast data sets. Data analysis isn't just for scientists in labs. It impacts our daily lives in profound and often unnoticed ways, making our existence more predictable and manageable. The universe itself is a grand experiment, constantly generating data. Every supernova, every planetary orbit, every collision of galaxies provides us with information. As humans, we have an insatiable curiosity, a deep-seated need to understand the why and how of things. Data analysis is the language we use to interrogate the universe and to understand our place within it. It helps us separate fact from fiction, to identify trends, and to make predictions about the future. It is the bedrock of scientific discovery and technological advancement. So let's embark on a journey to understand two fundamental ways we begin to decipher this data univariate and bivariate analysis. Let's start with the basics. The prefix uni means one, and variate comes from the word variable. So univariate analysis is simply the analysis of one variable at a time. Imagine you're an astronomer focusing your telescope on a single star. You're not looking at how it interacts with other stars just yet. You're just studying that one star in detail, its brightness, its temperature, its size. That's the essence of univariate analysis. We take a single characteristic, a single piece of information, and we examine it closely to understand its properties and patterns. It's the first step in getting to know our data. What kind of things can we study with univariate analysis? Think about the heights of students in a classroom. Height is the single variable here. We could measure each student's height and then analyze this set of measurements, or consider the ages of people attending a concert. Age is our single variable. We could collect the age of every attendee and then explore the distribution of those ages. Univariate analysis is about describing what that single variable looks like. It's about painting a portrait of that one characteristic, showing its features and typical values. The main goal of univariate analysis is to describe. We want to summarize the data and find meaningful patterns within that single variable. We're not looking for causes or relationships between different things at this stage. We are simply trying to understand the distribution of our data. How often do certain values appear? What is a typical value? How spread out are the values? These are the kinds of questions univariate analysis helps us answer. It provides a foundational understanding before we venture into more complex explorations of how different variables might interact with each other. For example, if a bakery wants to understand its sales of chocolate chip cookies, it might look at the number of chocolate chip cookies sold each day for a month. The number of chocolate chip cookies sold is the single variable. The bakery can then calculate the average number of cookies sold per day, find the day with the most sales, or see how much the sales vary from day to day. This gives the bakery a clear picture of its cookie sales pattern for that specific type of cookie, without yet considering factors like weather or promotions. This is univariate analysis in its simplest, most practical form. Let's explore some more real-world examples to make univariate analysis crystal clear. Imagine you're a doctor studying the blood pressure of your patients. If you collect the systolic blood pressure readings for 100 patients and analyze only these readings, you are performing univariate analysis. You might calculate the average systolic blood pressure, find the range, highest and lowest values, or create a graph showing how many patients fall into different blood pressure categories. This helps you understand the general blood pressure profile of your patient group. Focusing solely on that one measurement for each individual, consider a city council interested in the commute times of its residents. They conduct a survey asking people how long it takes them to get to work. The commute time is the single variable. The council can then analyze this data to find the average commute time, the most common commute time, the mode or the spread of commute times. They might discover that most people have a commute between 20 and 40 minutes. This information, derived from analyzing just one variable, can be vital for urban planning, like deciding where to invest in public transportation or road improvements, focusing on the characteristic of travel duration itself. Think about a coffee shop owner who wants to understand customer satisfaction. She asks customers to rate their experience on a scale of 1 to 5 stars. The star rating is the single variable. By collecting these ratings, she can perform univariate analysis. She might find that the average rating is 4.2 stars, or that 70% of customers give a 4 or 5 star rating. This gives her a snapshot of overall customer satisfaction based on that single rating metric. She's not yet looking at whether satisfaction is related to the time of day or the barista on duty, just the ratings themselves. Even in my field of astrophysics, univariate analysis is fundamental. When we discover a new exoplanet, we might first analyze its estimated mass. Mass is the single variable. We would look at this mass in isolation, perhaps comparing it to the mass of Earth or Jupiter to get a sense of its scale. Or we might study the distribution of temperatures on the surface of Mars, looking only at temperature readings from different locations. This initial focused examination of a single characteristic is a crucial first step before we try to understand the planet as a whole system or its potential for hosting life. So what specific insights can we glean by looking at just one variable? Univariate analysis primarily helps us understand three key aspects of our data: its central tendency, its dispersion, and its frequency distribution. These might sound like fancy terms, but they are quite simple ideas. They give us a powerful summary of what that single variable is telling us. Understanding these aspects is like getting the vital statistics of our data, painting a clear picture of its character before we explore further complexities or relationships with other variables. Central tendency tells us about the typical or central value in our data set. You've probably heard of the mean or average, the median, the middle value, and the mode, the most frequent value. These are all measures of central tendency. For instance, if we analyze the salaries of employees in a small company, the mean salary gives us an average, while the median salary tells us the point at which half the employees earn more and half earn less. This helps us understand what a common salary might look like within that specific group. Dispersion, or spread, tells us how much the values in our data set vary from each other. Are all the values clustered closely around the average, or are they spread out over a wide range? Measures like the range, the difference between the highest and lowest value, variance and standard deviation help us quantify this spread. If we're looking at exam scores, a low standard deviation means most students scored similarly, while a high standard deviation means the scores were widely scattered. This tells us about the consistency or variability within that single set of scores. Finally, frequency distribution shows us how often different values or ranges of values occur in our data set. We often visualize this using histograms or frequency tables. For example, if we analyze the ages of people visiting a museum, a histogram can show us how many visitors fall into different age groups. For example, 0 to 10 years, 11 to 20 years, etc. This reveals a pattern. Are most visitors young children, teenagers, or adults? Understanding the frequency gives us a clear picture of the shape and structure of our data for that single variable, highlighting commonalities and rarities. Section 5. Two stars, aligning, introducing bivariate analysis. Now, let's expand our view. What if we want to look at more than one star at a time? What if we're interested in how two stars might be related? Perhaps how their gravitational pull affects each other. This brings us to bivariate analysis. The prefix bi means two. So, bivariate analysis is the analysis of two variables simultaneously to explore the relationship between them. We are no longer looking at one characteristic in isolation. We are looking for connections, for patterns that emerge when we consider two pieces of information together. Imagine you are not just looking at the height of students, which is univariate, but you're also looking at their weight. Bivariate analysis would allow you to see if there's a relationship between height and weight. Do taller students tend to weigh more? Here, height is one variable and weight is the second variable. We are examining them in pairs for each student to see if they move together in some predictable way. This is the core idea, looking for associations or correlations between two distinct measurements taken from the same individuals or items. The primary goal of bivariate analysis is to determine if a relationship exists between two variables, and if so, to describe the nature and strength of that relationship. Are they positively related, as in, as one increases, the other tends to increase? Are they negatively related, meaning as one increases, the other tends to decrease? Or is there no apparent relationship at all? Bivariate analysis helps us answer these questions. It moves beyond simple description to explore the interplay between different factors, offering deeper insights than looking at variables one by one could ever achieve. For example, a company might want to know if there's a relationship between the amount of money spent on advertising and its monthly sales figures. Advertising spend is one variable and monthly sales is the second. By analyzing these two variables together over several months, the company can see if increased advertising tends to correspond with higher sales. This is a crucial step in understanding the effectiveness of their marketing efforts. It's about finding potential links, which can then inform strategic decisions and resource allocation based on observed connections. Section 6. Mapping connections, bivariate analysis in action. Let's delve into some real-world scenarios where bivariate analysis shines. Consider a health researcher studying the relationship between hours of sleep per night and daily stress levels. Hours of sleep is one variable, and stress level, perhaps measured on a scale, is the second. By collecting data on both variables from a group of people, the researcher can use bivariate analysis to see if there is a correlation. Do people who sleep less tend to report higher stress levels? This kind of analysis can point towards important lifestyle factors affecting well-being. Think about an agricultural scientist investigating the effect of fertilizer amount on crop yield. Amount of fertilizer applied per plot of land is one variable, and crop yield, for example, kilograms of corn harvested from that plot, is the second. By varying the fertilizer amount on different plots and measuring the corresponding yields, the scientist can analyze the relationship. Is there a point at which adding more fertilizer stops increasing the yield or even decreases it? Bivariate analysis helps find that optimal balance, directly impacting food production and farming efficiency. Imagine an economist looking at the relationship between the unemployment rate and the inflation rate in a country over several years. Unemployment rate is one variable and inflation rate is the other. Bivariate analysis, often visualized with scatter plots, can help identify if there's an inverse relationship, as suggested by some economic theories like the Phillips curve. Understanding such relationships is crucial for policymakers when they are making decisions about monetary or fiscal policy, aiming to balance employment and price stability for the nation's economy. Even in education, bivariate analysis is incredibly useful. A school principal might want to see if there's a relationship between student attendance rates and their final exam scores. Attendance rate, percentage of days attended, is one variable, and final exam score is the second. By analyzing these two for all students, the principal can determine if students who attend school more regularly tend to achieve higher scores. This can help in emphasizing the importance of attendance and developing strategies to support students who might be struggling with it, thereby improving overall academic outcomes. Section 7. Seeing double. What bivariate analysis uncovers. When we look at two variables together, what kind of insights can we uncover that univariate analysis alone cannot provide? Bivariate analysis primarily helps us understand correlation, which describes the strength and direction of a linear relationship between two variables. It doesn't necessarily imply that one variable causes the other, a very important distinction we must always remember. However, identifying a strong correlation is often the first step towards investigating potential causal links further down the line through more rigorous experimental designs. A common tool in bivariate analysis is the scatter plot, which visually represents the relationship between two quantitative variables. If the points on the scatter plot tend to form a line going upwards from left to right, we say there's a positive correlation. For example, as study hours increase, exam scores tend to increase. If the points form a line going downwards, it's a negative correlation. For example, as temperature decreases, heating bill costs tend to increase. If the points are scattered randomly with no clear pattern, there might be little to no correlation between the two variables. Beyond just seeing if a relationship exists, bivariate analysis can also help us quantify the strength of that relationship using a statistical measure called the correlation coefficient. This coefficient typically ranges from -1 to +1. A value close to +1 indicates a strong positive correlation, a value close to -1 indicates a strong negative correlation, and a value close to 0 suggests a weak or no linear relationship. This numerical value gives us a more precise understanding than just looking at a graph, allowing for more objective comparisons of relationship strengths across different pairs of variables. Furthermore, bivariate analysis can be used for predictive purposes, though with caution. If a strong correlation is found, we might develop a simple regression model. For example, if ice cream sales and temperature are strongly positively correlated, we could use the temperature forecast to predict approximate ice cream sales. However, we must always remember that correlation does not equal causation. Just because two things happen together doesn't mean one causes the other. There could be a third, unobserved variable influencing both, a lurking variable that clouds our interpretation if we are not careful. Section 8. Spotting the difference univariate versus bivariate head-to-head. Let's put these two types of analysis side by side to really highlight their differences. The most fundamental difference lies in the number of variables they examine. Univariate analysis, as its name suggests, focuses on a single variable. Its purpose is to describe that variable, to understand its characteristics like its central value, its spread, and how its values are distributed. It's like taking a detailed photograph of one object, studying all its features in isolation from its surroundings. It provides a foundational understanding of individual data components. Bivariate analysis, on the other hand, always involves two variables. Its primary purpose is not just to describe, but to explore the relationship between these two variables. It asks, do these two variables tend to change together? If so, how? Is the relationship positive, negative, strong, or weak? It's like observing the interaction between two celestial bodies, studying how they influence each other. It moves beyond individual characteristics to look at connections and interdependencies, which is a step towards understanding more complex systems. The types of questions they answer are also distinct. Univariate analysis answers questions like, what is the average height of students? Or what is the most common car color sold? Or how much do house prices vary in this neighborhood? It's all about summarizing and understanding one thing at a time. Bivariate analysis, conversely, tackles questions such as, is there a relationship between hours spent studying and exam scores? Or does temperature affect ice cream sales? Or do taller people tend to have larger shoe sizes? It seeks to uncover associations. Finally, the statistical tools and visualizations differ. For univariate analysis, we use measures like mean, median, mode, standard deviation, range, and visualizations like histograms, bar charts for categorical data, and box plots. These tools are designed to summarize and display the features of a single data set. For bivariate analysis, we use tools like scatter plots to visualize the relationship, correlation coefficients like Pearson's R, to quantify its strength and direction, and simple linear regression to model the relationship. These tools are specifically designed for examining pairs of variables. Section 9. Why this matters. The importance of analytical eyes. Understanding the difference between univariate and bivariate analysis isn't just an academic exercise. It's fundamental to making sense of the world around us, a world that is increasingly driven by data. Whether you're a scientist, a business owner, a student, or just a curious citizen, these analytical tools empower you to look beyond surface-level information and uncover deeper insights. They are the building blocks for more complex analyses, but even on their own, they provide tremendous value in our quest for knowledge and informed decision-making. Univariate analysis provides the essential groundwork. Before you can understand how things relate, you first need to understand the things themselves. Knowing the average income in a region, Univariate, is crucial before you try to analyze its relationship with education levels, Bivariate. It helps us identify outliers, understand distributions, and summarize key features of individual data sets. This descriptive power is the first step in any data exploration, helping us clean our data and get a feel for what we are working with, ensuring a solid foundation for any subsequent, more complex investigations. Bivariate analysis then takes us a step further, allowing us to see connections and patterns that we would miss if we only looked at variables in isolation. Identifying that increased exercise is correlated with lower blood pressure, or that higher customer satisfaction is linked to repeat business, can lead to actionable insights. While it's crucial to remember that correlation doesn't imply causation, these identified relationships often spark further investigation, leading to experiments or more sophisticated analyses that can help us understand the underlying mechanisms driving these observed patterns. Ultimately, mastering these basic analytical techniques equips us to be better thinkers and more informed citizens. In an age of information overload and sometimes misinformation, the ability to critically examine data, to understand its basic properties, Univariate, and its potential relationships, Bivariate, is a superpower. It allows us to ask better questions, challenge assumptions, and make decisions based on evidence rather than solely on intuition or anecdote. The universe is full of patterns, and these tools help us begin to decode them, one variable and then two variables at a time.